Hello. Please hit like button and subscribe my channel. Also press bell icon for future video notifications. Thanks.
Determining how rapidly the universe is expanding is key to understanding our cosmic fate, but with more precise data has come a conundrum. Estimates based on measurements within our local universe don't agree with extrapolations from the era shortly after the Big Bang 13.8 billion years ago. A new estimate of the local expansion rate, the Hubble constant, or H0, reinforces that discrepancy. Using a relatively new and potentially more precise technique for measuring cosmic distances, which employs the average stellar brightness within giant elliptical galaxies as a rung on the distance ladder, astronomers calculate a rate, 73.3 km per second per megaparsec, give or take 2. This means that for every megaparsec, 3 million light-years, or 3 billion trillion kilometers, from Earth, the universe is expanding an extra 73.3 plus or minus 2.5 kilometers per second. The average from the three other techniques is 73.5 plus or minus 1.4 kilometers sec, mpc. Perplexingly, estimates of the local expansion rate based on measured fluctuations in the cosmic microwave background and, independently, fluctuations in the density of normal matter in the early universe, baryon acoustic oscillations, give a very different answer, 67.4 plus or minus 0.5 kilometers sec, mpc. Astronomers are understandably concerned about this mismatch, because the expansion rate is a critical parameter in understanding the physics and evolution of the universe and is key to understanding dark energy, which accelerates the rate of expansion of the universe and thus causes the Hubble. Dark energy comprises about two-thirds of the mass and energy in the universe, but is still a mystery. For the new estimate, astronomers measured fluctuations in the surface brightness of 63 giant elliptical galaxies to determine the distance and plotted distance against velocity for each to obtain H0. The surface brightness fluctuation (SBF) technique is independent of other techniques and has the potential to provide more precise distance estimates than other methods within about 100 mpc of Earth, or 330 million light-years. The 63 galaxies in the sample are at distances ranging from 15 to 99 mpc, looking back in time a mere fraction of the age of the universe. For measuring distances to galaxies out to 100 megaparsecs, this is a fantastic method, said cosmologist Chung-Pei Ma, the Judy Chandler Webb Professor in the Physical Sciences at the University of California, Berkeley, and Professor of Astronomy and Physics. This is the first paper that assembles a large, homogeneous set of data, on 63 galaxies, for the goal of studying H-naught using the SBF method. Ma leads the massive survey of local galaxies, which provided data for 43 of the galaxies, two-thirds of those employed in the new analysis. The data on these 63 galaxies was assembled and analyzed by John Blakesley, an astronomer with the National Science Foundation's NOIR lab. He is first author of a paper now accepted for publication in the Astrophysical Journal that he co-authored with colleague Joseph Jensen of Utah Valley University in Orem. Blakesley, who heads the science staff that support NSF's optical and infrared observatories, is a pioneer in using SBF to measure distances to galaxies, and Jensen was one of the first to apply the method at infrared wavelengths. The two worked closely with Ma on the analysis. The whole story of astronomy is, in a sense, the effort to understand the absolute scale of the universe, which then tells us about the physics, Blakesley said, hearkening back to James Cook's voyage to Tahiti in 1769 to measure a transit of Venus so that scientists could calculate the true size O. The SBF method is more broadly applicable to the general population of evolved galaxies in the local universe, and certainly if we get enough galaxies with the James Webb Space Telescope, this method has the potential to give the best local measurement of the Hubble constant. The James Webb-Schpock giant elliptical galaxies. The Hubble constant has been a bone of contention for decades, ever since Edwin Hubble first measured the local expansion rate and came up with an answer 7 times too big, implying that the universe was actually younger than its oldest stars. The problem, then and now, lies in pinning down the location of objects in space that give few clues about how far away they are. Astronomers over the years have laddered up to greater distances, starting with calculating the distance to objects close enough that they seem to move slightly, because of parallax, as the Earth orbits the Sun. Variable stars called Cepheids get you farther, because their brightness is linked to their period of variability, and Type Ia supernovae get you even farther, because they are extremely powerful explosions that, at their peak, shine as bright as a whole galaxy. For both Cepheids and Type Ia supernovae, it's possible to figure out the absolute brightness from the way they change over time, and then the distance can be calculated from their apparent brightness as seen from Earth. The best current estimate of H0 comes from distances determined by Type Ia supernova explosions in distant galaxies, though newer methods, time delays caused by gravitational lensing of distant quasars and the brightness of water masers orbiting black holes, all give around the same number. The technique using surface brightness fluctuations is one of the newest and relies on the fact that giant elliptical galaxies are old and have a consistent population of old stars, mostly red giant stars, that can be modeled to give an average infrared brightness across their surface. The researchers obtained high-resolution infrared images of each galaxy with the Wide Field Camera 3 on the Hubble Space Telescope and determined how much each pixel in the image differed from the average. The smoother the fluctuations over the entire image, the farther the galaxy, once correct. Neither Blakesley nor Ma was surprised that the expansion rate came out close to that of the other local measurements. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.